So this is a movie of a metallic glass under load. We have all seen a glass break. So the main point that I wanted to make here is like this glass breaks very, very like suddenly and catastrophically. I mean, once a glass is broken, it's gone. I mean, so this sort of a brittle behavior of a glass is what makes it difficult to use in many places, even though they have some conducive properties. So is the I would like to begin from some experimental background of my work. So it has been known that the fracture in glasses propagates via cavities. So here you can see this is a glass which is being loaded this is a metallic glass, and when you load it, these are the morphologies that you encounter during the fracture of the glass. So you can see that like there are some small holes which sort of coalesce, and they coalesce and then form a whole crack in the glass. So this has been seen in multiple experiments. So this is one recent experiment where they have observed this in many different types of glasses, the phenomena of like fracture propagating via coalescence of cavities. So now I'll give a little bit of background of what are these cavities. I'm going to stress mainly upon these cavities. So this is the phase diagram of a glass forming system in the temperature density plane. So as you can see that there are like lines separating liquid and the gas liquid coexistence region. So if you're below the glass transition line in the liquid, you have a glass, and if you are below this temperature, a glass transition temperature, where this line cuts the binodal line, you have a gas-glass coexistence region, because the liquid that you have is a glass or a solid at that point. So this gas-glass coexistence is what is sort of responsible for the cavitation, which was shown in the previous slide. This is one of the studies of cavitation in simulations. So this is a study by Pinaki. So what they have done here is like they have taken they're starting from a high density glass, and they expand it into this gas plus glass coexistence region. And as they expand it into this gas plus glass coexistence region, we see like cavities forming in the solid, and this has been done at finite temperatures and finite strain rates. So there are some hysteric effects as well that they have shown here, but these are not very important to what I'm going to talk about, so I'll come to that. So this is another study by the group of Smarajit, and here they are looking at the fracture mechanisms under confinement. So these are hard walls on the right, and there is free boundary in this direction. So they are looking at like what kind of that they are doing uniaxial loading, and they are looking at what kind of morphologies that you get. So what they are seeing is that at low aspect ratios you have this necking kind of failure, whereas at a high aspect ratio you see this cavitation and the failure via cavitation. So these cavities are appearing here as well in these studies. So now I'll quickly give you the outline of the work that I'm going to present. So in the first part of the work, I'll be talking about these instabilities under uniform expansion. And in the second part, I will show what happens to these instabilities if you have, say, multiple modes of deformation combined. So I'll talk about the first part first. So what we are doing is we are doing particle-based simulations. We are using the standard 2D Cobb-Anderson model, which has Lennard-Jones potential, and you have particles in 65-35 ratio. We have also checked this phenomenology for many other models in 2D and 3D. So we prepare an initial glass by cooling a liquid in MD simulations from a high temperature to some low temperature at some cooling rate. The cooling rate that we have checked a few more cooling rates as well, but the phenomenology is broadly the same. So what you do is like we start with a high density glass prepared in MD, and in each step of the simulation, we strain the simulation box and then minimize the energy. So this is like athermal quasi-static expansion. The strain is the volume strain. So we expand the box and minimize the energy. So this is like taking the strain rate to 0 and temperature to 0. So we are in the athermal quasi-static limit. So I'll start with the results. So when we start with the high density glass here, we expand it. So this is the curve that is followed. This is pressure and this is density. So as you can see that on expansion the pressure is decreasing, and beyond a point you see some yielding like criteria. So the different curves are for different system sizes. And if you look at the individual trajectories, this is the one individual trajectory and this is the average trajectory. So you can see that there are pressure drops, sudden pressure drops. These pressure drops correspond to cavities forming in the solid, and as you expand more and more, you see that these cavities propagate through the system, leading to complete fracture of the solid. We also look at the fluctuations of the pressure at different density. So we characterize the fluctuations using a susceptibility, which is defined as the variance of pressure times the n. N just subtracts out the Gaussian nature of the fluctuations in this regime. So what we see is that the susceptibility curves for different system sizes, as the system size increases, you see a sharper and sharper peak at this main first event that you have here, first cavitation event. And we see that the peak of this susceptibility goes as n, and this has also been seen in the studies of athermal quasi-static shear. And if you see for the large system sizes, there is also another secondary peak here. So this peak corresponds to the growing of these cavities and sometimes even complete fracture of the solid. This movie has not been read. I'll just quickly show the movie. So this is the movie of the simulation. So the solid is being expanded, and as you expand, you see these cavities, and these cavities merge and ultimately fracture the whole solid. So I'll just go back to the presentation. So now we are looking at so as I told you, these cavities grow via pressure drops. So one natural thing we were trying to look at is like what happens on the potential energy landscape. So to see what is happening on the potential energy landscape, we look at the Hessian of the potential energy in the simulations, and we find that near each instability, the lowest non-zero eigenvalue goes as a power law, which is by the exponent 0.5. So here you can see these are the lowest eigenvalues of the Hessian, the lowest non-zero ones. So near each pressure drop, you see these eigenvalues going to 0, and they go 0 by a square root law. So these different curves correspond to different models here, and so in the context of plasticity under athermal quasi-static shear, this is linked to saddle node bifurcation on the potential energy landscape. So basically what is happening is like your system is residing in some potential energy minima. As you strain it more and more, this minima becomes unstable, and ultimately it becomes like flat. So the second derivative is sort of going to vanish here, and it vanishes as a power law. So this power law has been seen in the context of amorphous solids under all kinds of deformation in some sense after our study. So I'll also talk about the eigenmode of the lowest eigenvalue, which I showed you in the previous slide. So what we see is like when you're approaching that pressure drop, the eigenmode is sort of like predicting the displacement field near the pressure drop. And as you encounter the pressure drop, you see that this is the field across the pressure drop, the displacements. So the displacement field near the plastic drop is well predicted by the eigenmode. So the overlap is around 0.99, 99%, and whereas here it's just 57%. So this is happening perhaps because of the cascade nature of the drop. So there are multiple pressure drops that it goes through at the same time. This is also like some sort of avalanche nature in drops. So now we also look at the statistics of the pressure drops and the energy drops. So first thing I would like to point out is that there is no steady state under the expansion because you're fracturing, whereas under the shear you have a steady flow state. And what we see is that the statistics of the pressure drop and the energy drop, they collapse onto each other if you scale by the exponents 0.34 and minus 0.53. So these exponents are different from the AQS, where under athermal quasi-static shear, the exponents are 0.33 and minus 0.66. So these exponents are different, but you still see a collapse of the distributions. And the means of these distributions follow these same exponents, 0.53 and minus 0.34. So this was the first part of our work, and coming to the second part of the work, we are trying to do a combination of deformations. So what we do is, like during our expansion trajectory, we pick up some states which are like spatially homogeneous, and we subject these states to a secondary deformation, which is, say, something like cyclic shear. So basically Peter has talked about cyclic shear yesterday. So you start with a straight box, a square box, and you shear it up to some amplitude quasi-statically, and then you come back to zero, and again you go in this direction, and then again come back to zero up to same amplitude. So we subject these homogeneous states to cyclic shear, and this is one protocol that we are doing under additional deformation. The other protocol which we are doing is basically we are trying to do local random deformation by activity. So the matrix is a solid, and we are just introducing activity to, say, 2% of the particles which are chosen randomly, and these active forces are provided by an extra force term that you add. So this kx is plus or minus 1, and this switches a direction after persistence time, and so after every persistence time you change the signs of case, and we make sure that there is no net momentum given to the system, and yeah, as I said, there is a persistence time here. So coming to the results, so what we see is that the cavitation starts occurring at much lower density. So this was a trajectory of pressure. We subjected these homogeneous states to cyclic shear. In this case, you can see that like the pressure starts dropping here itself. So these are the density field plots. So this was the cavity under expansion which was forming here, whereas these four correspond to these four drops. So ultimately what one sees is that with alternate mode of deformation you can sort of have these instabilities occurring at much lower thresholds in some sense. So similarly for the activity, we see a very similar behavior, and a very, very same phenomena here. This is at a very low temperature with activity. So now coming to the phase diagram. So the cyclic shear can be done with different amplitudes, and the active force can have different magnitudes. So we summarize this in a 2-parameter phase diagram. So this is the amplitude of the cyclic shear, and these are the different densities. This black line corresponds to zero pressure line. So we see this cavitation under alternate deformation only when the system is below P equals to 0 line, and this green region represents the cavitation region, and the red part represents the homogeneous states, spatially homogeneous, and this black line that you see here is yielding under cyclic shear. So what we basically in both the cases we see that cavitation occurs at much higher densities and instead of expansion, I mean, as compared to expansion. So what we see is under cyclic shear, when the cavitation occurs, you see some system spanning plasticity. Okay, 3 minutes. Okay. Yeah, we see system spanning plasticity, whereas under local deformation via activity, you see that the plasticity is concentrated in one certain region, and so I'll quickly go through this slide. So what we are seeing here is that when you're doing cyclic shear and forming these cavities, the energy at which the cavities are formed under expansion, these energies are much higher than the energies that you encounter in the cyclic shear cycle. Similarly for the activity, the energies that you encounter are much smaller than the energies at which the cavitation occurs under expansion. So suggesting that like your barriers to cavitation are much smaller for the secondary deformation in the expansion state. So I'll just quickly summarize what I've told. So basically we have seen that the cavitation instabilities occur via same mechanism on the potential energy landscape, which is saddle node bifurcation. So this has implications in understanding that near a point of plasticity, or say under a point of near the point of cavitation, how the moduli and all vanish. So which I have not discussed now because of the time constraint. And we have also seen that the avalanche statistics of the cavitation instabilities have a scale-free nature. So they go. You just have to scale the distributions by some exponents and you get back the distribution for a larger system size. So, and then we have seen that like the thresholds for observing cavitation are lower if you have a secondary mode of deformation, suggesting that under cyclic shear and under activity, the cavitation instabilities couple very well in some sense than the expansion as a mode of deformation. So that's it. Thank you.
Thanks, Umang. Questions, comments?
Yeah. So maybe you said it, but the initial configuration that if it's a poorly annealed or a well annealed one, does it change the way?
So yeah, I have not talked about it, but if the most what I've checked the phenomena for slightly well annealed this thing as well, but I've not talked about it here. So I mean, it's just that this point will shift, and the curve will shift a little bit here and there, but the phenomena exists.
The nature of cavitation.
The secondary deformation still causes cavitation.
After the expansion, suppose you just started to get this small cavitation, not the catastrophic one. Mm-hmm. So if you reverse your deformation, can you close them?
So the answer is mostly yes, but I mean it depends on how small you're talking about. Like so, I mean if there is just a one particle hole, will you call it a cavity or not? That's the question.
Okay.
But
is it reversible? Closed for more than one particle hole?
Yeah, so many of the main cavities will close down, but maybe there are some small holes that might remain.
Okay. And obviously those larger ones, they will, like if you reverse it back, it will be...
Yeah, it will shut down, yeah. These holes will shut down. Yes.
So, in your first slide, you talked about how these cavitations can be thought of as coming as coexistence between the solid and the gas phase. So, can you get the shapes and using some nucleation theory arguments and?
So we have not looked at it at the moment. So you're saying the critical size of the cavity.
Critical size, shape,
Yeah, so we haven't looked at the statistics of the size yet. But yeah, that's a good point. I mean, so we need to.
So typically in nucleation, it's a pretty rare event. So simulations. I mean, I'm surprised that you get. So, I don't understand.
The shapes.
How this is related to cracks, or is it related to cracks?
So basically, I mean, this is related to those small cavities which are formed.
Yeah.
So in that sense, like these cavities are causing the crack. That's the point.
Yeah.
And these cavities are sort of a manifestation of this. I mean.
But there's a whole body of work on cracks and nucleation theory and so
I mean that I don't understand well, but I think it's more on the bigger length scale, I thought.
Nice.
Yeah, here we had strictly at t equals to 0.
So is the crack.
Yeah. Yeah, I mean
theory.
This is actually more like nanoscale phenomena in some sense.
I see.
So I think maybe
could be more of a spinodal.
Yeah, after spinodal, right.
Okay, maybe we can discuss after that.
For instance, if you have a finite temperature, So would this instability, the saddle node which you have, would you still see those divergences?
So that is on the potential energy landscape. So strictly we are in T going to zero limit. So I mean, you have a free energy landscape in some sense at the finite temperature. So I mean,
But much of this phenomena would be sort of would continue, because that's also relevant.
yeah. So I think Pinaki has already done it at finite temperature. These results which you're seeing, these are already at finite temperature. I mean, which are at like around below the glass transition temperature. I mean.